Friends, let us continue the lecture on module 1. This lecture is lecture 12, where we are going to discuss about planar non-orthogonal structural analysis. Let us try to understand the application of this kind of problem in reality. We all have agreed and understood that if we have a single frame of a simple type, whatever may be the end support conditions, whatever may be the kind of loading, as long as the members are orthogonal to each other, we could do a very comfortable analysis by writing the stiffness matrices of all these members, finding the unrestrained stiffness submatrix, then find the end moments and end shears of each member, and we can solve the problem. To do this, we have to identify unrestrained degrees of freedom and then the restrained degrees of freedom of a given problem. These degrees of freedom can be displacements which are translational and rotational at every node. So, the method becomes more complicated when the structural members of the system are not at 90 degrees to each other. Let us see an example. Let us take for example the jacket structure or a jacket platform, which is also called as template structure, which is one of the offshore platforms which are meant for shallow waters. A typical view of this platform schematically looks like this. These are all different levels of deck, let us say multi-tier deck. They will be supported by some structural system. The structural system can even be a truss type, it can be a beam column type. There are now tubular members which are then extended to the seabed, which are then founded in the piles. So, this becomes my seabed, possibly this becomes my water level, mean sea level, and then they will also be braced. To resist the lateral forces arising from the wave, and then the superstructure will have forces which are encountered by the wind. So, therefore, look at the structural system which is supporting the top side. The members here are actually not orthogonal to each other. So, this angle is not 90 degrees. So, there is a possibility that the members are interconnected to each other, not at 90 degree, but at desired angles like a K joint, like a T joint, like a Y joint, where the members may not have all the time 90 degrees between them. So, such systems are called non-orthogonal structural systems. What is the difficulty with non-orthogonal structural systems? Okay. So, now we have a conventional equation of K, the stiffness matrix of the entire structure. I call this as Kc, where C stands for the complete structure, multiplied by the displacement of the complete structure is actually equal to the joint load vector of the complete structure plus end restraints generated for the complete structure. This above equation is valid only when the local axis system of the member and reference axis system of the complete structure matches. If this matching happens, then one can establish K in terms of submatrix by dividing them and partitioning them, then solving them for delta u, then m I, as we have discussed in the previous examples. When the reference axis of the system and the local axis of the members of the system are not same, they are not mapped, they are not aligned, then the stiffness matrix written for the member, for each member, may not be same as that of stiffness matrix written for the members which are not aligned with the reference axis of the structural system. So, we need to actually do some transformation of the local stiffness matrix to the reference axis system matrix and try to solve the problem. Let us see, the complication starts only when the members are non-orthogonal to each other. So, we can make a statement that all members must be aligned, if not aligned, transform. With respect to the reference axis. Individual stiffness matrices of each member should be developed in the same manner as we discussed earlier. So, there is no confusion in that. There is no confusion in that, but should be transformed within the frame of reference axis, some literature call the two axis systems as x and y, xm and ym. They call this as local axis system, and this is called as reference axis system. Some literature address this as global axis system. The meaning is going to be same. So, there has got to be a connectivity established between the local axis and the reference axis system to solve the problem. Whatever derivation we so far had for a member aligned along xm ym axis, that is the local axis system of the member, is all completely valid, but they need to be transformed when the local axis system is not mapped exactly to the reference axis system. If the local axis system and the reference system are one and the same, then the issue will not be there. That is possible only when the members are orthogonal to each other. When the members are non-orthogonal to each other, then the mapping of local axis system to the reference axis system is a major issue. We need to do this transformation not only one way, but it is vice versa. From local to reference axis we may have to do, sometimes from reference to local axis also we may have to do, because it is required for the design of the members. Okay, both ways we should have an idea how this can be done. So, now the stiffness matrix K I, what we have discussed so far are with reference to XM YM axis system. Okay. We can otherwise call this for our understanding as local axis system, where M is the index of the member. Okay. Now, each member, if you look at the standard notation we had, if this is the member, if these are the end supports of the fixed beam, if this becomes my XM and this is accepted to be my YM, and if this is my ith member, the member has got two ends. This end is called the jth end and this node is called the kth node. So, it is very interesting, one must choose the XM axis such that the length of the member lies on the positive side. What do you mean by this? Let us say I have a member which is fixed at both the ends. If I choose my XM here and YM here, the length of the member lies on the negative side of XM. So, this is a wrong notation. So, it all depends upon where do you locate your jth end of the member. Subsequently, the kth end of the member is located on the positive side of XM axis. YM axis is located anti-clockwise. Some literature address this as counterclockwise. Okay. It is one and the same, anti-clockwise by 90 degrees to XM. So, let us again draw a member. This is my member, these are the fixed supports of the member. I am marking XM and YM here, which is 90 degree anti-clockwise with respect to XM. So, this becomes my jth end, this becomes my kth end. So, all conditions are satisfied, like the length of the member is on the positive side of XM, J is chosen such that the length of the member lies on XM positive, YM is anti-clockwise 90 degree from XM and XM YM now becomes the member axis system, or otherwise also called local axis system. So, whatever derivation we have done for the ith member, the stiffness matrix derivation, all are valid for the local axis system. Okay. So, it is very important to note that choice of jth end helps to orient the member local axis to that of the reference axis. Okay. So, it is all depending upon where do you choose your jth end. We can give some example. Let us take two examples. An orthogonal system and members with non-orthogonal to each other. Let us say A, B. Let us mark the reference axis for both of them as same. So, this is x and y, for both of them it is same, okay, x and y, but the local axes are going to be different. Let us mark the member indices, this is the first member, the second member and the third member. Similarly, here the first member, second member and third member. Now, I want to mark the j and k ends of the first member. So, we know that I have to mark x m and y m this way, because the length of the member should be on the positive side. So, this becomes my jth end and this becomes my kth end of the member 1. Similarly, if you want to do it for member 2, this becomes x m of the member 2 and y m of the member 2. Therefore, this end becomes the jth end of member 2 and the kth end of the member 2. Similarly, for member 3, I have to choose the length of the member to be on the positive side of x m and y m is anti-clockwise 90 degree. So, this becomes my jth end, this becomes my kth end. So, choice of jth end actually helps us to orient the member with reference to the reference axis. Let us do this for this problem, which is shown in picture B. So, obviously, I am going to plan member 1. So, I can say this is my x m and this becomes my y m and this is my jth end, this is my kth end. And for the member 2, this is my x m, this is my y m and therefore, this becomes my jth end, this becomes my kth end. And for the member 3, I can either do it this way or the earlier way, like we have done for member 1. So, this is x m, y m. So, let me put a suffix, this is 1 indicating for the member 1, this is 2 indicating for the member 2 and this is 3 indicating for the member 3. It is not x m q and y m q. Okay. Y m 3 indicates this is for the member, this is the axis and this is the member ID. Okay. That is how it is done. So, orienting the member with reference to the global axis will happen by choosing the jth and kth end of each member. Okay. When the members are non-orthogonal, obviously you will see the local axis of the members are not aligned with the reference axis of the structural system, except for the member 2 it is possible. For member 1 and member 3 they are not aligned. So, member 1 and member 3 need to be transformed with a knot, because their axes are not getting mapped or aligned. Having said this,